Differential equations. So here is applications to real life. Often scientists are making observations on things based on rates of change. They see the derivative, they see how things are changing in real life, and they want to find a mathematical formula, which would be the antiderivative, working backwards, to describe their findings. So we call this equation of the form where you know the derivative equals something as a differential equation. So you recognize something, but now you want to go back in time and describe it overall with a model. Now, whenever we do a general solution, when we do this general solution, we add the plus c. But if you have some sort of information that you've also observed, an initial condition, like, oh, when we started, there were 300 mosquitoes in this room. We did an experiment and we saw how they're changing. Now there's this amount of change per hour, blah, blah, blah. We can use that initial condition, sometimes called a boundary condition, to actually solve what was the number c to begin with. So solving for c. If you have a differential equation, that's 2x. It's really easy to see the antiderivative was x squared plus c. That's our general solution. So in order to find the c, we would need an additional piece of information. Like, oh, the original parabola went through 0, 3. And then you'd be like, oh, my parabola has been moved up 3 units. So my c value would be 3. So here we have our differential equation, which is 3x. Find the general solution of that equation. Well, that would be 3x squared. Add 1 to the exponent and divide over 2 plus c. So then if it goes through the point 2, 3, that is on your original function. You can now find the actual equation. Start with your general equation, and you can plug in 2 and 3. And then you can solve for c, and you can write. We now know the actual equation because we were given an additional piece of information. So solving for that c is sometimes called finding the particular solution. Because there's a general solution has all of them with the plus c. A particular one is when you know a specific value of c. So in order to find a particular solution, you need an additional piece of information, that initial condition or boundary condition. So we know that if x equals 3, y is equal to -1, if this is our differential equation, we can integrate to find our original equation with the plus c, and then plug in things and solve for c. Once we've solved for c, then we can rewrite the particular solution with that value in there. So now we're going to go through some questions, just look at what is different ways to ask the same thing. Okay? Like if they give you dy dx, they're telling you this is the derivative. That made it straightforward. Look at how the wording changes slightly on this next question. The slope of a curve at a point. They're talking about the tangent line. The slope of a curve at a point is like the tangent line at an instantaneous point, that's a derivative. So how do we say derivative in a different form, right? So just to be aware of, what are they talking about? Okay, once you recognize that, hey, this is a derivative, it goes through this point, so I can find the integral to find the function. They'll have a plus c. Plug in my point, 1 for x, 4 for y, and solve for c. And then I can write my final equation. So try the next question. A little bit of problem solving. Try this one on your own. Check with your neighbor what answer they got. So from the diagram that's given, you can find your slope to be 2. You know your y-intercept is 3, so we've got the equation of that line. If we integrate that and remember the plus c, this is our general equation. We do have an initial condition. They tell us when x is 3, y is 11, so I can plug that in and find out c would be -7. So now my actual equation for f of x is x squared plus 3x minus 7. And if I want to find f of -3, I plug that in, and I get -7 as an answer. And sometimes we have higher order differential equations. Was that too fast? Was everybody done? Yeah, okay. Sometimes you might be given the second derivative and have to work back twice. When you work back once, you have a plus c. When you work back again, I have to do plus c again, but it sort of makes sense that you get in trouble if you use the same variable more than once in one equation. So we start numbering them. It would be like, well, the first time I go back, I'll call that C1. If I go back again, I'll call that one C2. I've seen some textbooks say, well, first time you use C, then what's after C? Next time, let's use D. As long as they're different. So I've got the second derivative. And it says find the particular solution. So it wants to find y equals, and it gives us a bunch of boundary conditions. If I work back once, I find my derivative. And so I'm using the C1 here because it's the first C that I found. And sometimes the question will give you information that you could actually solve for C1 already. It might give you a boundary condition for the derivative. It might say, when x is 3, the slope of the tangent line is 2. So then you could plug in 3 for x and 2 for dy dx. This one doesn't do that. It just gives us information about the original equation. So if I work backwards again, oops, here we go, work backwards again, then I would get a C2. Now there's two things that I don't know. I don't know C1, and I don't know C2. If there's two things you don't know, you need two equations in order to solve them. So in blue here, I said, well, if I plug in 0 and I get 1, well, it actually worked out really nicely that everything went away and you solved for C2 right away. But it could mean in this question we could have had a system of equations where you have two equations with two unknowns and have to use substitution or elimination, remember all of that, in order to solve the equation. But this one, when I plugged in boundary condition number 1, I found C2. So now when I plug in boundary condition number 2, I already know C2 is 1, and I can solve that C1 is a wonderful fraction of -74/3. Are you starting to notice this when you get into higher level math? That in lower levels, you sometimes got a number like -74/3 and you would have went, I must have done something wrong. No way the teacher would do this to me. Has that been beaten out of you? Like, yeah, okay, it's a funny looking number, but the teacher could do that to me now. I feel it's like, what the good old days when your answers were always like nice numbers. I'm sorry, I get creative sometimes, and I think of obscure things. I'm thinking of a multiple choice test where they gave you A, B, C, and D, but sometimes the answer might be in between things. So you have like a scale, and you might have to circle like 8.2-ish, somewhere in between, or like maybe A, B, and C were put on a circle, and you'd have to put a dot kind of like, well, it's mostly A, but it has a little bit of B and a tiny bit of C, but not D whatsoever. Where would you draw the dot on this? That would be very obscure. Sorry. I should have paused the video so my weird thoughts don't go online. I don't know. And so now we've got C1 and C2, we can write out what the final equation is. And can you see that if you take the second derivative, these last two things would just go away completely? And you would just have that 12x squared, which seems nice and simple. Feels kind of awkward to have that -74/3 in there, but it's okay. Here's another one, the second derivative. So if you have the second derivative, they're going to need to give you two pieces of information because you need one piece of information at least to solve for C1, another piece of information to solve for C2. Sometimes you might get two equations with two unknowns and have to work with that. That could be possible. So I work backwards once. Life is good. I take the derivative of that and I get my C1. What is your derivative? Your derivative is slopes of tangent lines. Did they tell us anything about the slopes of a tangent line in this question? Yes. They said the slope or the grade of the curve at the point P is 23. So what does that mean for this equation? If we know the slope is 23, that makes me think I can replace the 23 with f prime, because that's the slope. What do I replace x with? 2, because it's at the point P, and the x value at point P is 2. So I can plug in 2 for x, and the 23 for the derivative, and that lets me solve for C1, which means I now know the particular solution for the derivative. Working backwards from there, integrate again, and now I'm going to have a C2 because I already used C1. Do we have any information about f of x that could help us solve this? Well, the point is on the curve. That means it's on the original curve. So when x is 2, y is 13. And if we do all the mental math for this, we're going to get C2. Kind of the nice thing in notes with like this that we don't have to worry too much about doing. I know you could do that mental math, so we could just like copy down quickly because it's not very hard. But now that we've got C2, now we can write the particular solution for f of x. So I'd like you to try the application question at the bottom on your own. And that's where we'll end for today. Oh, you did. So here is like a real life example of how differential equations could be used. You might be recognizing how fast the population has grown. And you might have had some data from previous years. So someone stocked a fish pond with 200 fish. They've been noticing the rate of change is a certain amount. And you're in year 5. And you look at your data and nobody wrote down how many fish there were at the end of year 4. So now you have to do some math to figure it out. So what we can do is we can integrate, add 1 to the exponent and divide. Remember the plus c, that's our general solution. From there, we can plug in our initial. And what's really nice about a lot of initial situations is that the value is 0, making your mental math lovely. So c is 200, which then gives us this as our particular solution. This is the actual model for how many fish there are at any given time. So we can plug in 4 and say there would be 4,000 fish.
Excuse the interruption.
1,000 fish.
Just a reminder for all students volunteering tomorrow at Valentine's School, go